Log on, tune in, find out. Another good idea from Cambridge.
Welcome from me, everybody. I'm David Wallace. I'm the director of the Newton Institute, and I'm really delighted to see you all here. Thank you very much for coming. It looks like a great program, and this is a really interesting workshop, obviously, to start it off. So I guess the first thing that I have to say is that I'm really, really grateful to the organizers to get out to Meinhold, who's here, and also to Sasha. Sasha, I'm not sure if I've seen, but I know Sasha is also here. So thank you very much for the effort that you put into this and into the scientific program. It looks really great. A few of the sort of routine words about safety and such. Please note the fire action required. There are 3 doors in this in this particular room. One thing I should say is, if you are upstairs, you should be aware that if there were a fire in the main area of the building, the main stairs are not a fire exit. There are 2 fire exits in each of in these 2 corners of the building. So please be aware of that, because they may not be obvious to you. The only other thing I would say on safety, we are quite a big group here. Please be very careful if you are powering up a laptop or something with a trailing cable. If people tripped over it, etc., it could be pretty bad. So I just ask you to be aware of trailing cables. And the final thing, well, maybe one thing, you know that we now record on video all these talks, and the microphones mean that you can contribute. So if you're asking a question, just speak up and you will be heard, and you will be there for posterity on the web. Finally, the whole role of all of the staff in the Institute is simply to facilitate and support your work. That's why we are here. If there is anything that you need to know, that you want to ask about, an issue that you have, please just go to the reception and ask, and they will do their very, very best to help you and to make sure that your stay here, however long it is, whether it's just for the workshop or for the whole program, is as enjoyable and as fruitful as it possibly can be. I think that's enough from me, because you're not here to listen to me, you're here to listen to the first talk. So I'm going to hand over to Meinhold, who will be sharing the rest of the session. I hope you have a really great time here at the Newton Institute. Thank you all very much.
Okay, I also wish to say welcome to the Institute here and to this first 2 instructional weeks. I was asked to alert you to some of these safety instructions. So one here is about fire alarms. The obvious thing, you have to leave the room, and there's one exit. And the second thing is, since all lectures will be video recorded, so there are some number of things here to observe for that. Maybe the most important is that mobile phones should be switched off, because this might interfere with this recording equipment. I think that's the basic things to announce. And then I think we can start the scientific program. So our first speaker will be Pramod Achar about derived categories and perverse sheaves. I just want to say, since some people asked me already, so every afternoon we have these discussion sessions. So these discussion sessions are really meant to be a complement to the lectures. So it may happen that in some lectures there will be exercises, examples, where there's not enough time to work them out during the morning sessions, and this afternoon should give the time and the occasion to expand a bit on the material of the lectures. So usually all the lecturers will be there during these discussion sessions and open to questions or remarks about the lectures. So I think if there are no questions from you, then I hand over to you.
Okay. Okay, well, thank you very much. So maybe I'll move this out of the way. So in fact, I'm planning to give some exercises. So I put them on my webpage, and I've put some there right now, and I'll probably add a few later in the week. So this is www.math.lsu. Maybe I'll write that in capitals also. /tilde dcps.pdf. So DCPS is derived categories and perverse sheaves. Is this legible to everyone? And then my plan for the week is something like this. So today I want to just introduce generalities about derived categories. Tomorrow will be T-structures, and I think we won't get to the definition of perverse sheaves until tomorrow. And then towards the end of Tuesday and Wednesday, we'll talk about some properties of perverse sheaves. And then the main topic for Wednesday, my plan is D-modules and the Riemann-Hilbert correspondence. Let's see. Thursday, I think I'll talk about weights, purity, and the decomposition theorem. And then I think, Friday, I mean, of course, the reason all of this is interesting and useful is that it has important applications in representation theory. I'll probably talk about various applications as we go along, and there might be some more of that left for Friday. And then depending on sort of how far we get on the other things, and if there's time on Friday, I might try to say something about perverse coherent sheaves, which are sort of a different but parallel theory to the usual perverse sheaves. Okay. So anyway, so let's get started. So the basic setting is going to be that A is an abelian category. The usual things are, you know, the category of modules over some algebra, or well, maybe the most important category for abelian category for this series of talks is the category of sheaves on some topological space, say sheaves of vector spaces. Is this large enough? Should I? Okay. Okay. So the sort of main problem that we want to try to address using derived categories is the fact that many sort of useful common functors fail to preserve exact sequences. So SES is what I'm going to write for short exact sequence. Well, of course, that's a problem because short exact sequences are what you use to understand the structure of objects in your category. And so, keeping track of the failure of exactly how these functors fail can give you useful information. So the classical way to do this was with derived functors, and derived functors are older than derived categories. So maybe I'll remind you a little bit about how that works. So the classical approach is with derived functors. Maybe the first derived functor that most people encounter are the xth groups. So xth n of, say, A and B. Well, so this is supposed to be measuring the failure of exactness of Hom, and here's how you compute it. One, you replace the second object B by an injective resolution, or you can replace the first one by a projective resolution. So let's call that I dot. So that's going to be some complex like this. I0 goes to I1, I2, and so on. And then and then we'll compute Hom of A with this injective resolution. So now this is in the second variable, there's a whole chain complex of objects, but it makes sense certainly to apply Hom to that. And then the answer that you get out of this is naturally itself a chain complex. Okay, so so maybe let's give a name to the terms of that chain complex. So let's name it like this. So maybe the first term will be M0. So that's Hom of A into I0, then M1, and so on. So here Mn just means Hom A comma In. And then, well, now you have a chain complex, and then the last step is just take cohomology of this chain complex. So take the nth cohomology of this complex of m's, and that's the answer. So that's xn AB. Okay, so so what we want to do now is take some kind of fancier approach to this. And the fancier approach should certainly, I mean, it should encompass the classical approach. We shouldn't lose anything. Maybe the motivating idea for the fancier approach is instead of replacing a single object by this injective resolution, I mean, when you do this kind of thing, you have to prove various things along the way. Injective resolutions are certainly not unique, so you have to make sure that taking a different injective resolution doesn't change the answer you get down here way at the end, and so on. So in the fancier approach, what we want to do is replace the category by a new category in which B is just isomorphic to this complex as an object. And of course also to all other injective resolutions. Well, so the first thing you notice is that, of course, the objects of the category, I mean, it's not enough to consider single objects of the abelian category anymore. Some objects are going to be actual chain complexes. So in fact, we're gonna just take all objects to be chain complexes. So all objects of this new category. Well, this is the derived category, of course. So all objects of D of A are chain complexes of objects of A. And I'm going to adopt the usual convention here, which is that all chain complexes go up. What I mean is that the differentials in a chain complex go up in degree rather than going down. So we're always going to talk about cohomology rather than homology. Okay. Well, B itself, well, objects of the original abelian category, we're going to think of them as objects in the derived category as just being chain complexes in a single degree. So chain complexes in 1 degree, and namely they're going to be in degree 0. So B, this object B means that the chain complex with zeros everywhere except in degree 0. Okay, and well, so to make this into a category, of course, I have to tell you what the morphisms in this category are. So that's going to take a couple of steps. So let me make a definition first. So a map of chain complexes. So let's call it F from C to D. So C and D are both chain complexes here, and F is some map which respects the differentials in both of them. A map of chain complexes is called a quasi-isomorphism. If it induces isomorphisms when you take cohomology of both chain complexes. So if all so you can take the cohomology of the map, which goes from Hn of C to Hn of D. So all of these should be isomorphisms. Okay. Okay. So here's how you define morphisms in the derived category. Well, what you do is you take all the ordinary chain maps that you already have, so just maps of chain complexes. So take all maps of chain complexes. And now what I'm going to do is formally invert all quasi-isomorphisms. So this is some kind of localization kind of procedure. Of course, the big problem here. Well, I guess first I should say that this is the correct thing in terms of motivation, because, well, the first thing we wanted was for an object of the abelian category to be isomorphic to an injective resolution of itself, and well, the map from an object to its own injective resolution is a quasi-isomorphism. So this is correct as far as that's concerned. But of course, the big problem here is that inverting a whole bunch of maps in a category is something a little bit mysterious. I mean, now a general morphism in the derived category isn't, well, it's not something that you can write down in terms of sort of elements of a chain complex. It's formally some word where you write down a list of ordinary chain maps, and then formal inverses of quasi-isomorphisms along the way. So the first problem is to figure out what the set of morphisms in the derived category between two chain complexes actually is. Okay. Well, I'll give an answer to this question. I'll give kind of an answer to this question in a few minutes. But first, I want to impose a restriction. Usually, we won't work with the full derived category, but instead with the bounded derived category, which just means, well, it's the subcategory of the derived category where you take the objects in which whose cohomology vanishes except in infinitely many degrees. So with hn equals 0 for n, let's say, very large or very small. Okay. So maybe one way we could try to do this is, well, we could just well, we want to do something with these chain complexes. So let's make a guess. Earlier, I guess on the board that's up there, we applied hom to an object and a chain complex, and then you got a chain complex out of it. This hom has chain complexes in both variables, but you could still, you could take hom sort of term by term. So maybe let's try and combine them. So here's the guess. It's going to take a couple of steps. So first is form the chain complex. I'm going to write this as underline hom. And we're going to abandon this notation pretty soon. But this is going to be a chain complex whose nth term, so I'll write a superscript n there, is the direct sum of a bunch of ordinary hom groups of terms of the C and D complexes. And then the terms that we're going to add up are those where j minus I equals n. And then, well, sort of, I called this a chain complex. So maybe a baby exercise here is to figure out what the differential is in this complex that makes it into a chain complex. And then here's step 2. Well, now here's a chain complex, and sort of chain complexes are the world we're working in. We want an actual group, so let's just take some cohomology. So let's take the 0th one. So H0 hom C D. Okay. So so here's what turns out to be the case. If under certain circumstances, this is the right answer. So if we assume that either the second variable is a complex of injective objects, or that the first variable is a complex of projective objects. Then that guess is correct. So then hom DACD is that group up there. So it's the zeroth cohomology of this underlying hom. And this has another interpretation also. If you're already familiar with derived categories, you might think I skipped a step over here. Often when you define derived categories, before inverting all quasi-isomorphisms, you mod out by chain homotopies. You don't actually have to do that because somehow inverting all quasi-isomorphisms causes that to happen for you automatically. But this cohomology group has this has another interpretation, which is that it's homotopy classes of chain maps, of chain complex maps from from C to D. Okay, so basically what this says is that to figure out what the morphisms in the derived category between two complexes are, well, you can do it concretely as long as you replace either the second one by a complex of injectives or the first one by a complex of projectives. Okay, so this is sort of resembling what we did with the X groups, which was on the first board. So in fact, well, let's go back to that X calculation. So X and AB, this is back in the notation that we used when we were talking about this. That was supposed to be the nth cohomology of the complex we got by taking a hom of A with the injective resolution of B. This is how we wrote it back then. I could stick an underline on this hom with no problem, just by regarding A as a chain complex in degree 0, like we normally do. Well, this is an Hn. I could change that to an H0 if I just change the numbering of the chain complex that's inside. So I'm going to change this to H0 of underline hom A I dot, and then I'm going to put a brackets n here. So brackets n means shift the indexing of the chain complex by n. Okay. So now what we've got inside these parentheses is an underlying hom of two chain complexes, and the second one is a complex of injectives. So, according to this proposition, what's in this whole thing just is a hom group in the derived category. So here's what we've got now. What we've discovered is that the X group, this sort of classical derived functor, is just an ordinary hom group in the derived category between A and, well, this complex of injectives, but that complex of injectives is isomorphic to B, but there's a shift. Okay. So this is sort of, well, this is one thing which is sort of typical of the kind of thing that goes on, that sort of classical derived functors like X are somehow built into the structure of the derived category, and it turns into an ordinary Hom group. Okay. Okay, so here are some observations about this. So the first one is that the derived category or the bounded derived category is usually not an abelian category. So what this means is that the usual familiar ideas like kernel or surjective, these have no meaning. And this is one thing that takes a bit of getting used to. And it seems like it's a bit counterproductive, because somehow I said at the beginning that the point was to deal with this failure to preserve exact sequences. And exact sequences have everything to do with words like kernel and surjective. So we'll come back to this in a moment. So one of the exercises that's on that web page is to show that a derived category, which is abelian under mild assumptions, contains only the zero object. So it really can't be abelian. Okay, so the second observation, which is going to sort of help us deal with this problem, has to do with the snake lemma. So I'll remind you what this says. And of course, this is one of those things which is sort of the kind of thing that everyone has to prove for themselves once in their life. And so if you haven't done that, you should. But anyway, here's what it says. So you take a short exact sequence of chain complexes. So now, of course, if I'm using the word short exact sequence, then it must be the case that I'm talking about honest maps of chain complexes, not derived category maps, because this is supposed to be injective and that's supposed to be surjective and so on. And what the snake lemma says is that a short exact sequence like this gives rise to a long exact sequence in cohomology. So when you take the cohomology of all three terms, you get something like, well, HNC maps to HND maps to HNE, and then that maps to HN plus 1C, and then it continues. And of course, sort of all the sort of famous long exact sequences of algebraic topology or whatever arise in this way. And this map, well, this is often called the boundary homomorphism or something. It doesn't come from a map of chain complexes. That's pretty easy to see in just about any example. But the magic thing is that it does come from a map in the derived category. So it does come from well, so it's going to be a map from E not to C, but since there's a change in degree in cohomology, we have to shift the indexing by 1 to make it come out right. It does come a map from E to C shifted by 1 in the derived category. So when you write down that map together with the original map, you get a diagram that looks like this. So the map from C to D is the same as the original map, and same from D to E. And then we have this extra map. This is not, well, that last map is certainly only in the derived category. It's not a map of chain complexes. So now it no longer makes sense to talk about exactness or whatever. But this particular diagram, this is an example of what's called a distinguished triangle. And distinguished triangles are sort of the, which I guess normally I'll write dt. Distinguished triangles, I guess, are sort of the I don't want to say the basic computational unit, but sort of maybe the basic unit of reasoning in a derived category. And many kinds of derived category computations sort of come down to understanding how to manipulate distinguished triangles. So sort of morally, distinguished triangles are the replacement for short exact sequences, and they're so they're the basic unit of thinking or something in the derived category. Okay, so so since we don't have concepts like kernel and surjective that we're familiar with, we need some rules. I mean, I said we're going to manipulate distinguished triangles, so we need some rules that tell us how we're allowed to manipulate them. So here's a list of some properties of distinguished triangles. And these are all things that well, these are things that require proof, but they're they're kind of routine. They're kind of diagram chasing kinds of things. And these properties have pretty standardized names. I guess these come from the thesis of Verdier. So they're called TR1 through TR5. And I guess, well, I'll tell you what TR stands for in a little while. So the first one is that, well, it's a specific example of a distinguished triangle. So if you take any object in the derived category and write down its identity map to itself, then the map to the zero object, so this is the zero chain complex, and then map to A1, then that is a distinguished triangle. Okay. TR2 says that any morphism in the derived category can be embedded in a distinguished triangle. So maybe I'll say completed to a distinguished triangle. The truth is, I haven't actually told you what the definition of a distinguished triangle is. I gave you an example, and in the example I wrote down the first map in the diagram was actually an injective map of chain complexes because it came from that short exact sequence. This is saying that doesn't have to be the case. So let me make a side note here about what happens in general. I mean, F need not even be a map of chain complexes, of course. It could be any morphism in the derived category. But if F is a map of chain complexes, then the third term in the distinguished triangle, which is called the cone of F, I mean, one has to take this statement with a grain of salt, but maybe it's a place to look for some intuition. The third term kind of contains both the kernel and the co-kernel of f. Well, it contains the co-kernel of f, and it doesn't quite contain the kernel. It contains the kernel of f shifted by 1. And the word contains is in quotation marks because it doesn't, for example, make sense to say that these things are subobjects of C because kernel and co-kernel are not defined in the derived category. What does happen is that if you want to write down a formula for the cone, then somehow pieces of both of these show up in the formula. Okay, and then the next one is quite different from what you normally do with short exact sequences. It says that you can rotate a triangle, and what that means is that a diagram like this is a distinguished triangle if and only if. Well, let me give these maps names. So F, G, H. I'm going to shift all the terms in position by 1. So now I'm going to have B going to C, going to A1, and then that has to go to B1. And then the maps here are, well, the first two are G and H. And then the last one here, well, it's a map from A shifted by 1 to B shifted by 1. So you can get a map between those two by shifting F by 1, and then you have to stick a minus sign in front of that to make all the calculations come out right. So minus F shifted by 1. So this is a distinguished triangle if and only if this is. Okay. So I think the last two, I think I won't write down right now. We might have use for them later in the week, and maybe I'll write down what those are. Both of them have to do with taking some kind of commutative diagram and extending it using distinguished triangles. So so these are about completing commutative diagrams with distinguished triangles. The fifth one is famous. It's the so-called octahedral axiom. Because well, it's called that because when you draw the diagram that the axiom involves, it's in the shape of an octahedron. And then so this list of properties, this is both a theorem and a definition. It's a theorem that a derived category, that the distinguished triangles in a derived category have all these properties. So let me write that down. So the distinguished triangles in the derived category have properties TR1 through TR5. But then the definition is that any additive category. Just to remind you, an additive category is something weaker than an abelian category. It means that the set of morphisms between any two objects is an abelian group, and you can add morphisms, and you can take direct sums, and that kind of thing. But you don't have things like kernels and the notion of surjective and so on. So any additive category with a specified collection of diagrams satisfying those axioms. satisfying TR1 through TR5 is called a triangulated category. So in other words, the theorem says that a derived category is a triangulated category. This week, we will come across triangulated categories that are not themselves derived categories. And the main way we'll do that is take a derived category and take some subcategory of it, which is not a derived category anymore, but still still obeys all these axioms and stuff. I think the notion of triangulated category is going to come up in some of the other talks later this week and next week as well. So anyway, so that's that. And then maybe in the time that's left, I want to talk about derived functors in the fancier setting. So here's the fancier approach to derived functors. And I think I'll sort of do this by example. So I'll talk about two specific derived functors, and then we'll sort of get some hint about how things work from those. So the first one I want to talk about is the derived functor of hom, which is called r-hom. And the r-hom, the letter r stands for right, because hom is already a left exact functor, so it preserves the left end of a short exact sequence, and we need to fix it up on the right, and that's what that letter r is doing there. So here's the definition of r-hom. Maybe this is not quite the definition. Rather, this is a recipe for computing r-hom. Okay. So the first is well, the first step is something quite familiar. We're going to either replace the second variable, replace d by a quasi-isomorphic complex of injectives, or you can replace the first variable by a quasi-isomorphic complex of projectives. Okay. I guess, in the derived category, of course, the words quasi-isomorphism and isomorphism are the same. But maybe since it's followed immediately by the word complex, it's better to write out specifically that I mean quasi-isomorphism. And then we're going to form this sort of complicated hom that we defined earlier, which is, I guess, not on the board anymore. But the underlying hom of these two complexes after we change one of them into something appropriate. And then, well, now this is a chain complex of abelian groups or vector spaces or whatever, depending on what kind of setting you're working in. And then, so just regard that chain complex as an object of the derived category of abelian groups or the derived category of vector spaces, whatever setting is appropriate. So this is almost what we did to compute X, or to compute hom groups in the derived category, except we didn't take cohomology. We just finished with the chain complex as an object. So here are some facts about this. Yeah, so I said we were going to abandon this underline hom notation. So now is when we abandon it. So from now on, we're going to write r hom, and r hom is going to have this sort of first step implicit in it. So here are some facts. So one is that r hom of CD, and the reason I really do need to regard this as an object in the derived category is that it's not well defined up to isomorphism as a chain complex, because you could take different injective resolutions or different projective resolutions, and then you'd honestly get different chain complexes here, but they're all going to be quasi-isomorphic to each other. So R hom CD is well defined up to quasi-isomorphism. So it really is giving you a well-defined object of one of these categories up to isomorphism. And second is that R hom is a functor. I mean, I've just been talking about objects, but you can have you can put in a map between chain complexes, or even a formal inverse of a quasi-isomorphism or something, and make sense of how to get a map between the corresponding R hom objects. So R hom is a functor, and it's not just any functor. It respects the structure on both ends. So what you're plugging in is two objects in the derived category of whatever abelian category you started with, and you're ending up in the derived category of abelian groups. And the structure that both those categories have is that they're triangulated. So they have some collection of distinguished triangles. And R hom takes distinguished triangles to distinguished triangles. So this is really, this fact is where we sort of achieve the goal of fixing up the lack of exactness of hom. So in the derived category, the replacement for a short exact sequence is a distinguished triangle, and this functor preserves them. Okay. All right. So here's another fact. This is a general fact, not about R hom, but it has to do with the snake lemma. Well, maybe this is kind of like a generalization of the snake lemma. And the fact is that taking cohomology takes any distinguished triangle to a long exact sequence in the abelian category. The snake lemma says that cohomology of a short exact sequence of chain complexes does that, and short exact sequence of chain complexes give you distinguished triangles, but those are not the only ones. There are other distinguished triangles also, and cohomology of any distinguished triangle gives you a long exact sequence. So here's the kind of thing you can do. For example, okay, let's say you want to apply the functor R hom A dot, so that A dot is a complex, and then blank in the second variable to the distinguished triangle C, D, E, C1. So then you get a distinguished triangle, which is well, it's a distinguished triangle in the derived category of abelian groups. which looks like this. Arham A E. And then I won't write down the last term. And now if you take cohomology, well, cohomology of Arham is just, that's how you compute Ham groups in the derived category. And then when you get to the end of the distinguished triangle, you'll have a shift of 1. So now when you apply H0, you get a long exact sequence of Ham groups, which looks like, so Ham AC, Ham AD, Ham AE, and then, well, I'll write down one more term. The term after that is Ham AC shifted by 1. And then, of course, you can keep going, and then on this side you would have negative shifts. So it's a long exact sequence of the kind that we're used to. So. Okay, so so maybe I'll talk about one more derived functor in the time that's remaining, and this is going to be relevant for the stuff about sheaves that we're going to talk about starting tomorrow. So what I want to do is look at the global section functor from the category of sheaves of vector spaces. On some topological space X to the category of vector spaces. So if you take global sections of a sheaf, you get a vector space. This is left exact, just like Ham. And then, well, you can take its right derived functor, and then that's R gamma. So that goes from the bounded derived category of sheaves on X, except normally, I mean, instead of writing dB of SH of X, I'll just write dB of X to dB vect. Okay. Well, here are some things you can do with this functor. We could apply it to the constant sheaf. So I'll write the constant sheaf on X with value, the complex numbers like this. So it's C underline X. And then, so then you get, well, OK, so what is that? So R gamma of Cx, that's some complex of vector spaces. Well, the way to understand what that is, well, what happens if you take cohomology of this? Well, this is what's ordinarily called sheaf cohomology. And then for nice spaces, this is the same as any other kind of cohomology you can think of. So this is the same as just the cohomology of X with complex coefficients. So for nice spaces, this could be singular cohomology, or if you're talking about a manifold, it could be de Rham cohomology. And so on. And here's what I want to do with this. I want to show you in a couple of minutes how to recover Poincaré duality from some machinery at the derived category level. And so this is called Poincaré-Verdier duality. And what Poincare-Verdet duality is it's a functor from dbx to itself. So from the derived category of sheaves on X to itself, which is an equivalence. Well, it's an anti-equivalence. It's contravariant, and the square of this is the identity functor. So if you take the dual twice, you get the same thing back. And well, here's in fact the definition. Well, I'll tell you the definition for a manifold, for an orientable manifold. D is R hom. So this is not the ordinary hom, but this is sheaf hom. Sheaf hom is left exact just like ordinary hom is, and then it gives you an object in the derived category of sheaves. So it's R hom blank comma the constant sheaf shifted by the dimension of X. Okay, so that's the definition. And then what I want to do is take Hn of the derived global sections of the dual of the constant sheaf. Okay. And there are two ways to analyze this. One way is, well, you could just compute this dual, and that takes some work. But then it turns out that the dual of the constant sheaf is the constant sheaf shifted by the dimension of X. So now if you're taking sheaf cohomology of the constant sheaf shifted by the dimension of X, that's just going to be ordinary cohomology with a shift. So it's Hn plus dim X of X comma C. But then the other thing you could do is figure out the relationship between these two functors, between Verdet duality and derived global sections. And it turns out that they more or less commute. So I haven't, I guess I haven't explained what it means to put D on the outside, because when you apply R gamma, you get something in the derived category of vector spaces. But putting D on the outside basically means putting a negative sign here and putting vector space dual on the outside. And then the isomorphism of these two, this is classical Poincare duality. Oh yes, compact, yeah. I guess this computation is for compact. Okay. So anyway, so that's it for today.
Thanks a lot. Are there any questions or remarks right now? All left for this afternoon. Okay, so we have a break for half an hour then.